Hi everyone, welcome to Heat Transfer course. I appreciate your interest to attend this YouTube lecture series conducted by TEQIP 3 faculty with the motive of Let's Crack the Gate. Before starting this today's lecture, I would like to introduce myself. I am Mohammed Rafi, one among the TEQIP 3 faculty from Department of Mechanical Engineering, Assam Engineering College. And I have done my MTech in Fluid and Thermal Engineering from IIT Guwahati and BTech in Mechanical Engineering from College of Engineering, Trivandrum. I am very much interested to utilize this opportunity to learn and share the thermal science knowledge, especially focusing on heat transfer. So in the first lecture, we have discussed about the relevance of heat transfer in competitive exam and also a brief introduction about the different modes of heat transfer. And in today's class, we will discuss the governing equation, different parameters involved in different modes of heat transfer and all. And one by one, we will be discussing each topics in the GATE syllabus, which is discussed in the last class. So if you are watching this course for the first time, please subscribe to this channel and support our effort. And also, there are some other courses also running parallelly, so watch those videos as well. So I hope this attempt, our little effort, will be helpful for you. So we are always free, feel free to discuss with us your queries, even in comment section or in the Telegram group. I hope you have already joined. Anyway, I hope this will have a very great interaction among us. So let's skip to the course content. Now, in the last class, we have discussed about the different modes of heat transfer, which is namely conduction, convection, and radiation. We have done this differentiation based on the mechanism of heat transfer. And in today's lecture, we are going to take one by one and analyze these modes of heat transfer. Now, you look at the diagram. Here, we are going to discuss about the conductive heat transfer. What is conductive heat transfer, how it is relevant, and how it is varying one by one. Now, suppose what is the definition of conductive heat transfer? It is heat transfer by means of molecular excitement within the material without bulk motion of matter. That is very important. Without bulk motion of the matter. So, if I am talking about the heat transfer is always between two object which is of different temperature, high temperature and low temperature. Suppose I am talking this solid is coming contact with the high temperature. That means it is getting heated up. And this is, suppose I am saying this is 30 degrees Celsius and this is heating with the temperature source of 100 degrees Celsius. So there is two objects, 100 degrees Celsius, 30 degrees Celsius, high temperature, low temperature. So we have already discussed whenever there is a temperature difference, there will be a heat flow. Which was the law in thermodynamics? Second law of thermodynamics, heat is always flow from higher temperature to lower temperature. So in solids, how this is possible? That is because of conduction. Now what is conduction? That is a mode of heat transfer without any bulk motion of matter. Now how this is possible? How it is possible? It is by lattice vibration as well as free electron transport. What is a free electron? In every solids, especially in metals, there will be free electron within the lattice. These all are the solid molecules. So there will be some free electron which is floating within the lattice. Now once I am started to heat, what will happen? These molecules getting heated up will start vibrating within the lattice. So while vibrating, you just imagine if I am asking 5 students are sitting on a bench. And if I am bringing one more student to that bench, what will happen? There will be some vibration. This is what actually happening in conduction. If I am trying to heat any solid, the molecules will start vibrating within the lattice. So whenever, if I just in the example of sitting on the bench, if I am adding a new person to that, then there will be some congestion. So it will again vibration means what? It is moving from one point to another. There will be a random motion here and there. So in the solid, this free electron, it will be excited and it will be floating within the lattice as well as these molecules will be vibrating each other. Thereby, this 100 degrees Celsius it will be moved, this 30 degree Celsius will become 35 or 45 or 50 by the time goes up. So there is a gradual variation of body temperature of the solid with the help of conductive heat transfer. The same process happens in the liquids and gases, but there is a difference because we already know the material molecules are arranged in different fashion. That is why we are differentiating solid, liquid, and gas. So in liquids and gases, instead of lattice vibration, there is no any restriction for motion. So instead of lattice vibration, there will be collisions and diffusions of molecule during the random motion. That is the main reason for the heat conduction. Now you already understood about the mechanism of conductive heat transfer. Now we are going to learn about the governing equation. What is a governing equation? I told you throughout our discussion in this course, our objective is finding out the like we already knew there is a heat transfer between two objects of different temperature. Now we are going to quantify. How to quantify? By using this governing equation. So for conduction, suppose you are imagine there is a block which is having a high temperature at one point and low temperature at another point. So we already know by mechanism, by lattice vibration, there will be some heat transfer taking place from higher temperature to lower temperature. Now how much heat transfer taking place, or what will be the temperature of some particular point at some particular time? These all are our objective. In order to do this, we have defined a governing equation. How these governing equations are defined? How this is defined? This equation usually in every engineering courses, the equations may be defined either by mathematical approach. We will start with some primary equation and we will apply some boundary condition and we will derive another equation. So similarly, there is another method, that is experimental observation. So this is conduction governing equations are observed by experiment. That is, scientists, especially Fourier people like Fourier, they have started to observe conducted a lot of experiment, and they started to correlate between the parameters. So here the main parameter is the heat transfer rate. So they observe it is directly proportional to the area and the temperature gradient. So from which they have defined the Fourier law of conduction, stating the heat transfer rate is directly proportional to the cross-sectional area as well as the temperature gradient. Now, in order to remove this proportionality constant, they have introduced a new parameter that is called thermal conductivity. Thermal conductivity. So, thermal conductivity, from this you can see thermal conductivity will have a unit of watt per meter Kelvin, because Q is in watt, area is in meter square, and temperature gradient will be Kelvin per meter or degree Celsius per meter. Here I am talking about the temperature difference. So it can be either in degree Celsius or in Kelvin. That doesn't make any difference, because whenever you say 5 degree Celsius temperature difference, so it is whether it is 5 degree Celsius or 5 Kelvin, both will have the same physical meaning. Right? So whenever you are talking about the temperature difference, then whether it is in Kelvin or degree Celsius, that doesn't matter. But if you are talking in the radiative heat transfer, there it will have some difference. I will discuss that in detail at that point of time. Now here, looking at the expression Qx, why there is a suffix called x? X is just simply denoting the direction of heat transfer along the heat transfer rate along the x-axis only. Just to make our discussion easy, I am restricting our discussion to a single dimension. That does not mean there is no heat transfer along other direction. Whenever there is a heat transfer difference, temperature difference, there will be heat transfer rate. Okay, so there will be x direction, y direction, z direction, a, b, c, any direction heat transfer can taking place. So in order to make our discussion easy, to make our analysis easy, I am just writing the expression for Qx in like this. Now you can see Qx, heat transfer rate along the x-axis. So A will be perpendicular to the x-axis, area perpendicular to that, and dt by dx, temperature gradient along the x-axis. If I am writing y, then it will be dt by dy. Okay, just remember. Another one is the negative sign. Why we are including a negative sign in our governing equation? It is simply denoting the direction of heat transfer. From the we already know from the second law of thermodynamics what is the direction of heat transfer. What is the basics of second law of thermodynamics? It talking about the direction of heat transfer. What is the meaning? Heat transfer taking place from higher temperature to lower temperature. So if I am taking that gradient, suppose in this direction, initially the gradient is taken the slope, right? It is just like the final value minus initial value divided by the difference. So it should be T2 minus T1 divided by suppose this is the breadth, then B. So which one is here? T1 is greater than T2. So if I am writing this expression just like this, then it will come out to be a negative value. So heat transfer cannot be a negative value because heat is flowing, right? So in order to make the analysis easy, I am intentionally putting a negative sign which doesn't have any value, any relevance other than it is denoting the direction. Okay, so throughout our discussion, whenever you are dealing with the heat transfer rate, make it as a positive value. Okay, now move on to the another very important aspect regarding the conduction, which is called that proportionality constant, which we call it as a thermal conductivity. Thermal conductivity. Why it is relevant? Because thermal conductivity is a physical property of the material. So physical property of the material. What is a property? Property is something differentiating among other material. For a human being, my body have a lot of property which will be different from your body. So that we can make a comparison. Suppose my weight, I am 70 kilogram and you are 100 kilogram. So you can say you are heavy, I am thin. But there is another person who is 50 kilogram. Then I will say I am heavy, you are light. So in order to make the comparison, you are defining a property called the weight of your body. Similarly, in order to make the comparison between the heat transfer, which is more conducting, which is not conducting, which is absolutely not at all conducting, in order to make all these things, I am defining a thermophysical property that is called thermal conductivity. So like I said, the unit of thermal conductivity is watt per meter Kelvin or watt per meter degree Celsius. That doesn't make any difference. Anyway, how this property is defined, how your weight is different and my weight is different, it depends on a lot of factors. What are the food you are eating, whether you are doing any excessive exercise or you are following any diet or you have some other parameters. Many factors are involved, right? Similarly, thermal conductivity also depends on many parameters, whether it is a material structure, material content, like this. So in order to understand this material structure, I would like to quote about the two material which is called a diamond. Diamond. Another is diamond and a graphite. Have you seen any diamond? Have you seen any graphite? Somebody might have seen, somebody might not have seen. Anyway, what is the relation? What is the main similarity between diamond and graphite? Both are made of carbon. Yeah, same material. Then if you measure the thermal conductivity, which one is more conductor? Which is more conductive? Yes, thermal conductivity of graphite is much higher than thermal conductivity of diamond is much higher than compared to the graphite. Okay, this is very important. Same material, but material structure is different. The crystalline structure is different for diamond and graphite. That is why both have the different thermal conductivity. Similarly, material content. That means if I make the comparison between the diamond and steel, both have different content, so it will have different thermal conductivity. Similarly, density of the material. If I am using a very heavy material, light material, both will have the different thermal conductivity. So the thermal conductivity of a material depends on different parameters. Okay, now let's try to make an analysis, just a comparison between the different parameters. So here I am showing a graph showing thermal conductivity which is increasing in this direction and operating temperature in this direction. So here you can see which one is the bottommost object. It is an argon or a gas, and which is a higher topmost thing, it is a diamond. So solid diamond got the highest thermal conductivity and gases got the lowest thermal conductivity. See, gases got the lowest thermal conductivity. and in between liquids are coming. Now again we can compare different types of solids. Suppose I am talking about a pure metal. For a pure metal means it is made of similar type of molecules. So if I am converting this pure metal into a alloy, how to convert? Nothing but I will include some foreign material. I am including some foreign material. Now I am starting to heat this. I am starting to heat this. So if I am starting to heat, what will happen? In solids, what is the mode of heat transfer? Conduction. How it is possible? Lattice vibration. So if I am putting some foreign material, definitely that lattice vibration will be hampered. There will not be that effective lattice vibration. So definitely its thermal conductivity goes down. That is why pure metal will be having higher thermal conductivity, alloy will have the lesser thermal conductivity. You can see all these things in the in this graph. And also there are some notable different exceptions like water. Suppose if I am increasing the temperature, initially water thermal conductivity increases, but later it is goes down because of its anomaly in the structure. But for gases, if you are increasing in general, if the gases, if you are increasing the thermal operating temperature, its thermal conductivity increases. Why? You can see, we already know how conduction taking place. Conduction taking place in the gases and all because of the collision. So if you increase the temperature, there will be a lot of random motion, there will be a lot of collision, so that it will increase the thermal conductivity. But in case of solids, if you increase the temperature, the vibration will be going down. So there will not be much heat transfer compared to the lower temperature. So here also you can see the same analysis I am just showing regarding the material content. For different material, we'll have a different. See, diamond got the highest thermal conductivity, and here a notable exception or notable factor is that mercury got the thermal conductivity higher than the solid, like gas, glass and brick. So mercury is the highest conductive liquid, diamond is the highest conductive solid, and similarly you can see mercury, we are using mercury in our thermometer. Why we are using mercury in thermometer? Because of its high thermal conductivity. And also there are other parameters like response time, its volume expansion. We will be discussing about all these things while we are discussing unsteady heat transfer, where we will discuss about the time constant of a thermometer. In our day-to-day life now, during this pandemic also, we are coming across a lot of type of thermometer. You might have seen infrared thermometer, non-contact thermometer and all. So thermometer, mercury thermometer also very much relevant in our day-to-day life. So we will discuss why mercury is used and how thermometers are operating. Now another mode of heat transfer which is called radiation. This is also a different type of heat transfer. We already know based on the mechanism we are classifying different modes of heat transfer. So radiation is taking place with the form of electromagnetic waves. Electromagnetic waves is a set of waves which is having a particular range of wavelength and frequency. We can classify these electromagnetic waves in the order of their frequency or wavelength. We will discuss in detail in the upcoming slides. So since the mechanism is different, definitely the governing equation also will be different. So it is very important to remember radiation got a lot of day-to-day life application, starting from the energy source of universe, that is sun is emitting the heat in form of electromagnetic waves, and earth is absorbing, all other surrounding planets are absorbing this heat energy, and they are utilizing or they are storing this heat energy for different purpose. And we are also using radiative heat transfer in our day-to-day life, whether we are using a microwave oven or we are using heating process for cooling and in winter season and all. Anyway, we are going to discuss one by one how it is different, what are the governing equation and all. Okay, now let's try to analyze the governing equations for the radiation. Just like I told in the conduction, here also some the scientists Tiffany and Boltzmann, they started to do some experiment, and they observed some similarity between the parameters, and thereby they have defined the expression for heat transfer rate in radiation. So they observed that heat transfer rate was proportional to the area, surface area, as well as the fourth power of temperature in Kelvin. This is very important. In radiation, temperature should be always taken in Kelvin. Otherwise, you will get a wrong answer. Anyway, what I wanted to convey is that for all the body which is of having some temperature, it will start emitting electromagnetic wave in form of some photons. Okay, everybody, you, me, everybody which is emitting, it will be continuously emitting heat energy. But are you feeling any tiredness by emitting heat energy? No. Why it is not? You are not feeling. You are not feeling. No, you will not agree. I am not emitting any radiation. No, you are also emitting. I am also emitting. This computer or this mobile or all other body which is of having any temperature, it will be emitting. How much heat energy emitting? That is the question. How much quantity of heat transfer taking place, or how much you are emitting at the same time this body is also emitting, so you are receiving as well, so that make the difference. You are emitting heat energy, you are absorbing heat energy in radiation, but what is the quantity? That is told by this expression, q equal to f sigma a t1 to the power 4 t to the power 4. So you can see these two body which is of high temperature, you can see this is hot body, this is cold body, both are interacting heat energy. So what is the heat transfer rate? Net heat transfer rate is given by this expression. Now let's analyze the parameters involved. This one f is called a view factor or shape factor, which depends on the geometry and surface property. We are going to discuss in detail about the view factor. It is very interesting area and it is very important in the GATE exam. I can see last few years continuously questions are asked in any of the set from you may be knowing that GATE exam have different set of question paper. So in every year there will be some question from view factor, and exams like DRDO or ISRO or state level exam also, there are multiple questions asked in the previous year question, and we will be discussing about all these things in the upcoming classes. Another interesting aspect is the sigma value, that proportionality constant, just like the thermal conductivity or the convective transfer coefficient. Here the proportionality constant is the sigma value. So what is the value of that constant? For constant, the value is 5.67 into 10 to the power minus 8. How to remember this thing? How to remember this thing? Just to remember 5, 6, 7, 8. So you guys should remember sigma value, that is the Stefan-Boltzmann constant value, what? 5.67 into 10 to the power minus 8. Don't forget, okay? 5, 6, 7, 8. Okay, that is a value. Now here it is minus 8. That is why you will not feel any energy loss, or because our body temperature is 37 degrees Celsius. So if I am converting 37 plus 273, so this much to the power 4 will be the heat transfer into 5.67 into 10 to the power minus 8. So this is very small value, 10 to the power minus 8. That is why you are not, the quantity of heat transfer will be very less. But if you are talking with a high temperature, then it will be appreciable value. It will be more than conduction or convection. Anyway, let's move on to the next mode of heat transfer, which is called a convection. So what is the difference? What is the major difference between convection and radiation? You may be knowing, right? What was the major difference between the convection and radiation? It is quite, you should notice only one difference is that more bulk molecular movement is there in the convection. There is a bulk molecular movement, but in convection there is no bulk molecular motion. So again, this convection you can classify into forced convection and natural free convection. How it is different? Again, let's go back to the kitchen, right? In the first lecture, we were talking about the making of tea while we were discussing different modes of heat transfer. Now let's try to, tea is already ready. Now let's try to cook a boiled egg. Anda to khayega na sab log. Anyway, even if you don't interested to eat egg, let's talk about the boiling a potato. Anyway, whatever may be the issue, let's stick on to the theory, the heat transfer concept. So what you will do in order to make a boiled egg? Yes, let's I will teach you how to make a boiled egg now. And the last class I will talk about the biryani. Kerala biryani, Malabar biryani. Okay, so one by one, starting from tea, then boiling egg, then Maggi, then tea, then biryani. Everything will be taught in the heat transfer class, so that even if you are stranded somewhere during the lockdown time, you can cook yourself and have a nice meal. Enjoy the meal. Anyway, I'm just joking. What I'm saying, talking about the boiling of the egg, what how you will do, you will just take the ambient water in the pot, the same pot you were using for making a tea. There is some ambient water, you will heat that water, you will put the egg into that, and you will keep for a couple of minutes, so it will be heated up, and you will take the egg outside. And then there comes the difference. If you are in hurry, what you will do, you will put that egg into water, cold water or something. If you are not in hurry, what do, you can keep it on the table and you can enjoy watching movie or something and come back after a while and eat it. But if you are in a hurry, either you will use some external force, either you will use some fluid, either you can use a fan or something to enhance the heat transfer. If you are using any external fan or something like that, then it is called forced convection. If you are doing heat transfer with the natural method without any external help, then it is called natural convection. So there is a major difference in convection, forced convection and natural convection. And we will discuss all the governing equations related to this. And it is very interesting to notice that forced convection and natural convection have a different governing equation. It's a kind of a complicated discussion. That is why I am keeping this topic. Convection will be discussed at the end of this session after completing conduction and radiation. But believe me, those who are following these lectures regularly, by that time you will be learned many of the factors related to thermodynamics, fluid mechanics, engineer mathematics, as well as conduction and radiation. So convection will not be that difficult. Okay, so let's move on to just analyze this diagram here. Just the same thing, cooking or heating your tea, making a tea. What you will do, you are heating water, so the bottom is getting heated up. Yes, it is getting heated up. I am getting heated up. Yes, it is heated up. So I cannot stay there. Just imagine you are visiting a hotel, they are making a paratha. How they are making a paratha? After cooking an egg, I am going to make a paratha. What they will do, they will have a pan, they will have a rectangular pan, and the gas stove is getting heated up, and they will make paratha. One here, two here. How many of are here? Yeah, I will eat three paratha. Yes, three paratha is there. So what they will do, this sheet is very hot, so they will put on the paratha on this, and they will heat both sides by using the shovel. Then what I wanted to say is that you are visiting that hotel and that guy is not preparing any paratha, but this surface is very hot. If you are by accident, you touch on the surface, what will be your initial reaction, your reflexive reaction? What you will do? Huh? You will get excited. You will just jump. The same thing happen if you are heating water molecule also. Everybody have the same reaction towards heat. They cannot hold it. They will just jump it. So whatever water molecule or any fluid molecule coming contact with the hot ambience, what they will do? They will start moving upward, because if you just simply take the gas equation, if the temperature is increased, density goes down. So it may not be applicable for all fluid, but for better understanding, I am just quoting this expression. So temperature is increased, density goes down. So the lighter molecule goes up, heavy molecules goes up. So what is the lighter molecule here? Warmer molecule. Water molecule goes up, cooler water molecules goes down. So there is a yes, water bulk molecular motion. That is why we will call it as a convection. We will not call it as a conduction. But if somebody asks you in any interview whether it is a conduction, what are the modes of heat transfer? So if you understood this much, you should have the enough confidence to say there are two modes of heat transfer: conduction and radiation. What about the convection? You can defend yourself. Convection is a part of conduction. It is almost same. right? So don't worry, even if you say there is three modes of heat transfer: conduction, convection and radiation, that is also true. And even if you say conduction and radiations are the two modes of heat transfer and convection is a part of conduction, that is also true, because people have different opinion and we are in a free country. We can have different opinion unless and until you are able to convince or you are able to justify your answer. Okay, so let's move on to the governing equations of convection. So in governing equations of convection, it is contribution by the famous scientist, yes, Newton. Just like in any other field, Newton have given an enormous contribution in heat transfer also in the form of convective Newton's law of cooling. So here, just like in the conduction, heat transfer rate was observed to be depending directly proportional to the area of surface area and also the temperature difference T1 minus T2. So this temperature difference we express in either in degree Celsius or in Kelvin and area in meter square. So in order to avoid this proportionality constant, I am introducing a new terminology that is called convective heat transfer coefficient, which is having a unit of watt per meter square Kelvin. What was the unit of thermal conductivity? It was watt per meter Kelvin. So here it is meter, it is meter square. We will come up with the expression critical radius of insulation. There we will use this concept, units of convective heat transfer coefficient and thermal conductivity. So we are going to discuss about this thing in the upcoming classes. Anyway, let's just like the thermal conductivity, let's explore the property called thermal convective heat transfer coefficient. So here it's a notable exception. Notable point is that this is not a property of a material. Wow. Convective heat transfer coefficient is not a property of material. That means you cannot differentiate material based on the convective heat transfer coefficient. Why it is so? That is the beauty of convection. There is a bulk motion of fluid particle. That means for any object, suppose you are talking about a metal rod having a thermal conductivity, so that you can term this much is the thermal conductivity of a metal rod, and you are using that metal rod for some purpose in conduction. But in convection, you use the same metal rod in different surrounding. Suppose here you can see it is mentioned it depends on the thermophysical properties of the fluid. Suppose you are using that metal rod in air, so that air will have a different density. But you are using the same metal rod in liquid or water, which will have a different density, or which will have a different viscosity, or which will have a different velocity. If you are going for a free convection or forced convection, in all this occasion, it will have a different H value, convective heat transfer coefficient. H value simply denotes the convective heat transfer rate. So that is the beauty of convective heat transfer coefficient. It is not a property of the material. It depends on the different parameters. So you can see from the range convection, forced convection and free convection. Forced convection will always have a higher thermal heat transfer rate. Another interesting thing you have to notice here. Here I have you note two things: condensation and boiling. Why? What is the relevance? These all are the phase change process. So if somebody asks you what is the mode of heat transfer in phase change, yes, it is nothing but the convection. Convection is the mode of heat transfer. It is not the conduction or radiation. Okay, let's move on to the solving a problem. Before starting solving the problem, I just wanted to, this is our first question I am going to solve in the classroom. So whenever you are coming across of any problem in my classes, what you have to do, you just pause the video. Just pause the video, read the question, try to answer and make mistake. Yes, what I am saying? Make mistake so that you refer to the answer I am saying, doing, so that you can rectify your mistake. I am just joking. Even if you don't make a mistake, that will increase your confidence. But even if you make a mistake, don't worry, try to rectify, because this is the place you wanted to know your weakness, you wanted to rectify your weakness. Okay, so now move on to this question. So for every competitive exam, it is final answer is our concern, not the steps. So you need not to draw the diagram and write all the details and all. In competitive exam, as much as possible you try to skip the slides, so that skip the steps, so that you will get the answer in a faster mode. So everybody pause this question and try to read this question and answer it. I am just trying to solve it by myself. So here there is a Q generation, and heat is generated within the solid and it is convected outward. Q convected, and it is given what is the ambient temperature 25 degree Celsius. I will name it as T infinity, and T1 is the surface temperature. So now the question is, what is the surface temperature? What is the surface temperature? So T1 is what? So in order to solve this thing, I will just use the conservation energy, or the second law of or the first law of thermodynamics, that is energy neither created nor be destroyed, but it can transform from one form to another. So whatever heat energy is reaching to this point, it should be convected. There is no wastage of heat energy. Now what I will do, Q generated should be Q convected. That is the meaning of conservation. So what is the total heat generated? It is given already 4 into 10 to the power 7 watt per meter cube. So into volume will give the total heat generated, and the total heat convected we use the Newton's law of cooling, HA T1 minus T infinity. Now 4 into 10 to the power 7, and volume of the cylinder pi r square into L should be equal to H into what is the area, surface area, 2 pi r into L, and T1 I don't know, minus 25, right? So in order to H I can write 1000. So solving this thing, cancelling all the common parameter pi r L and writing all the other parameter, 4 into 10 to the power 7 into r 5 into 10 to the power minus 3 equal to 1000 into 2 into T1 minus 25, and solving this I can write T1 will be 125 degree Celsius. So like you may be knowing, for GATE exam the final answer will be there are different types of questions, multiple choice questions, or numerical type question, or what, or multiple choice question. So multiple answer question. So in order to answer this question, you should, if it was a numerical type question and you have been asked to give the answer in Kelvin, but you have got the answer degree Celsius, so you have to add with 273. Okay, so you will get, what is the answer, 398 Kelvin. So that is the answer here. But if it was multiple choice question, here it is already given the options in 2015 GATE set number 2 with the 2 mark. But if it was a multiple numerical type question, be aware about the units. If it is asked in degree Celsius, it is answer is 125. If it is asked in Kelvin, it is 398. Okay, now I am stopping here. Like I said in the last class, we will be consider it as a introductory class, and in the next class onwards I will be discussing a lot of previous year questions, and stick with this strategy so that you will also benefited from our effort. So please share this video, subscribe to our channel, and I wish all the very best to everyone. Stay healthy, stay safe. Thank you.